Now that we really understand some of the base components and fluids, let's talk about pressure regulation and the devices that we're going to use to regulate the pressure inside the system. If it gets too much, you could damage things that are in that system. That's not really, it's defeating the purpose of the hydraulic system. If it's too low, then we won't be able to actually do what we want to do with the hydraulic system. You press your foot on the brake and nothing is going to happen. Nothing's going to stop because there's just no pressure there. Okay, so we're going to start our discussion about pressure regulation with flow control valves. Now, these valves simply just dictate which way the flow of hydraulic fluid is supposed to go. Now, the graphic that you have in front of you is out of the 8083. It's really simple. Depending on where that piston that's on the bottom of the graphic is positioned, there's different pathways for the hydraulic fluid to go in. Now, one of the simplest examples of this is actually not a hydraulic system, but it is like your fuel control. Like if you're flying in a little GA airplane, you can have your fuel selector on either left, right, or both on most airplanes. That means it's drawing from the left tank, the right tank, or both tanks. Now, what it makes that selection possible is a flow control valve. You can either take fuel from just one tank, or you can take fuel from both tanks or the other tank. Hydraulic systems have a very similar type of construct, type of device that allow for the hydraulic fluid to flow from one system into the next system, or in one direction, but then turning around and reversing the flow so it flows back the other way, which allows you to have a lot of versatility on which way that fluid is flowing. So therefore, where the force gets applied is kind of the so what. So that is a flow control valve. Now, the most common application of a flow control valve is going to be like in your servo actuators, and we'll get to what those are at a later time. Essentially, they allow a hydraulic system to move something like a flight control, or in our case, the landing gear, inside the aircraft to outside the aircraft, from the up position into the down position. Now, in order to be able to have that versatility to go backwards and forwards, you have to have a servo that can extend or contract, and then you have to have hydraulic fluid that can pressurize the extension or the contraction. Well, you don't want to have two separate hydraulic systems, one for the extension and then one for the contraction, and then even if you did, you'd have to deconflict, or they would be fighting each other. So a flow control valve, and in this case, a servo actuator control valve, allows the flow of fluid to be changed, so that way the hydraulic actuators work one way, and then they, with the same amount of power, can work backwards the other way. So in our scenario with landing gear, the actuators are going to push the landing gear down into the locked position, but then it's also going to have to grab it and pull it up whenever we pull the landing gear up. So the flow control valve serves a vital portion of this action. Okay, probably one of the most important valves to remember when it comes to hydraulic lines or hydraulic systems is the check valve. The check valve essentially just allows fluid to flow one way and not the other. The way it does that, there's a little ball valve on there with a plate behind it, and as pressure is applied to that plate, it compresses a spring, allowing fluid to pass around the ball and plate and spring, and then down through the line. Now, whenever the fluid or the flow reverses and comes back the other way, the exact opposite happens. On the back side of that plate, there's pressure is applied that seats the valve and seals the line, and not allowing any hydraulic fluid to escape back the way that it came. Therefore, making sure that the hydraulic fluid only goes one way. Now, with these check valves are all over the place, and they allow us to create isolated systems, so that way fluid can enter in but can't come back out. When you combine this with the flow control valve, you have a lot of really cool options that you can do with hydraulics. Okay, so another valve that helps us, regulate having the right pressure, the right place, at the right time, is a sequence valve. All a sequence valve really does is allows us to ensure that the right pressure is applied to the right place at the right time. So the kind of classic example is that you want the landing gear doors to close only after the landing gear is up and locked. Once the landing gear is up and locked, then the doors can come up and close and be fine. Now, if the sequence valve wasn't there, what would end up happening is that you would eventually get an out of sequence actuation where the landing gear doors would want to close on the landing gear that's still down and locked, and you're going to end up damaging something. So a sequence valve allows you to mitigate that problem. Now, what you're seeing in front of you is a pressure controlled sequence valve, and this is actually pretty simple. You buy it. There's an adjustment screw on the outside of the valve that allows you to increase or decrease the tension that's on the spring that sits on top of this piston. Now, depending on how much tension's on that spring, it will move the piston up or down and divert a certain amount of fluid at different stages of the game, thus changing the level of pressure that eventually gets applied to whatever is on the outlet side of the sequence valve. And so you'll see these all over the place, and the same kind of this is in terms of hydraulic sequence valves, but this same sort of setup will happen all over the place. That there'll be a small little adjusting screw that you have to turn to change the pressure or the flow rate or something on any sort of device that has fluid flowing through it. This just happens to be in a sequence valve. Okay, so another type of valve that you may come across is a mechanical sequence valve. This one is pretty cool in my opinion. If you look at the graphic here, you're going to see how they work. On the left hand side, you have the plungers fully extended. So imagine like your gear is fully extended, or it's down and locked, and there's not a way for the hydraulic fluid to flow from port A down and out through port B. Okay. However, whenever the gear is up, and so that plunger comes in, it collapses that check valve and allows for fluid to flow from port A all the way through to port B. Now, in this scenario, you would think that port B also runs another actuator for, say, like the gear doors or something to that effect. That allows that sequencing to actually happen. But notice that it integrates the sequence valve with the check valve with the mechanical aspects of the plunger and spring. Pretty neat. And what's cool about it is that how simple it actually is. People think hydraulics being like super duper complicated, and really it's pretty simple once you kind of start breaking it down to the individual components. Okay, so another type of valve in terms of pressure regulation that is going to become very, very important once we kind of get to the end of hydraulics, when we start looking at a 737's hydraulic system, is the priority valve. Now, the priority valve essentially says, hey, look, whenever pressure is low, then certain systems are going to get prioritized over other systems. So let's say you have a hydraulic leak, the fluid starts to go out, and as the fluid leaves, there's less fluid in the system, pressure starts to drop. As pressure starts to drop, this is where the priority valve comes in. Notice the set screw on the very, very top of the system. That allows you to change the spring tension inside of that priority valve. Now, with the greater tension, that means that the spring wants to expand as much as it possibly can, so it's going to take a lot of hydraulic pressure to collapse it to allow it to get to the secondary system. Now, if the pressure starts to drop, the secondary system will get cut off, and the primary system will still be allowed to function. Now, the reason why this is important, there are certain systems where you want to have control all the time. Like you want to have maximum hydraulic pressure right there all the time. So like say your flight controls. If you can't control the flight controls, you can't control the plane, you're going to crash. However, there's other random things that maybe they're not as big of a deal. Let's say, like, I'm not gonna say that this is one of them, but let's say your gear door. Well, like, the gear doors, like, at the end of the day, the flight controls are the priority, and the gear doors are just help there to help streamline the plane as it flies along. If we have to, we can belly land the plane. So if we're gonna have to choose between the gear doors and the flight controls. We're gonna choose the flight controls. So you can look at this graphic here and say the secondary system is the gear doors and the primary system is the flight controls. And as the hydraulic pressure starts to drop, then the first thing that's going to get cut out is going to be your gear doors. But like, it's going to have to get below a certain level before the flight controls lose hydraulic pressure. Okay, so let's talk about quick disconnects. So these are actually two valves that meet up together. Now, why would you need a quick disconnect? Well, there's a couple of scenarios where you may need to disconnect the hydraulic system. So, like, if you were to say you're doing some sort of maintenance, what you don't want to have to do is crank the engine or turn the battery power on or whatever to run hydraulic pumps to pressurize the system. So they have a cart that they'll roll up next to the aircraft and then connect it up there, and that supplies hydraulic power directly to the aircraft. And the way that it attaches to the airplane is through a quick disconnect port. And so basically, it allows to a aviation ground power unit like we used in the Army, or a thing called the Mule, to connect directly to the aircraft hydraulic system to provide that hydraulic pressure, so that way you can still actuate flight controls, swing the gear, do all that sort of thing. Now, the way that it does that, now if you had to disconnect a line every single time and put like a T fitting on, that would be pretty bad. It would increase the much higher chance of contaminating the system. It would be expensive in terms of just time, and then you have all these other components that are mixed in. And so the quick disconnect allows you to simply just collapse a poppet valve and then on both sides, and then you effectively have a new component that's been introduced into the whole system that supplies pressure. Now, we actually use these pretty extensively on in the Army on the OH-58, because if we ever had to do any sort of flight control work, we had two hydraulic quick disconnects on the right hand side of the helicopter that we would disconnect, and then we would just hook up our aviation ground power unit, or our AGPU, directly to the system, pressurize the hydraulics, and then we could go on from there, troubleshooting whatever issue we'd have. We use it frequently to find leaks. Right? Like, there's a lot of things that you could do with it, but like, what I remember the most is actually hooking up the AGPU and then turning the hydraulic pressure on and looking to see where the leak was at. You'd clean the flight deck up really, really nice, turn the AGPU on, and then wherever you start to see the little red drips of 5606, that's where you went and started working on it. Yeah, so that is a quick disconnect valve. It's a really cool little device. Okay, so another neat device is a hydraulic fuse. Now, what a fuse does is allows for the system to be closed off if there's also this downstream drop of pressure. So as long as pressure is, say, like, if 100 is the regular operating pressure for the hydraulic system, so like on the upstream side, if the psi, or the pressure, is still at 100 psi, and then on the downstream side, all of a sudden it drops off to, say, like 80, the hydraulic fluid fuse closes and preserves that system. Reason being is, what they don't want to have happen is that if there's some sort of like leak or burst, or something happens, a bird strike takes out a hydraulic actuator or what have you, you don't want to just eject all of the hydraulic fluid into the atmosphere and then leave the plane basically not able to be flown, because the hydraulic system is basically broken down. So the hydraulic fuse basically works kind of like a tourniquet, like out on the battlefield. If someone gets shot in the leg, instead of having all of their blood dump out through their femoral artery, you'd put a tourniquet on there to say, like, hey, look, we know the leg's in bad shape, we may lose it, but we'll save our life if we just maintain if we collapse that femoral artery and keep the blood inside their body. The hydraulic fuse works much the same way. You can think of it as kind of like a tourniquet for a hydraulic system. Okay, up to this point, most of the devices we've talked about in terms of pressure regulation have been for what happens if the pressure gets too low, like hydraulic fuses or what have you. But here's the question: what happens if the hydraulic pressure gets too high? What device do we have that can help regulate the pressure from getting just out of control? 'Cause you could think that like if the pressure were to get too high, things could burst, lines could crack. I mean, you name it. There's all kinds of things that could happen. Your components are going to get messed up, whatever. So one of them is a pressure relief valve. Now, this pressure relief valve works like a regulator, pretty simply, where pressure comes into the valve. It has to then go around a ball that is pushed down on by a compression spring, which is then pushed down by an adjusting screw. Now, the state of that ball will either it basically kind of works like a faucet in your bathtub or whatever. It constricts the flow of the hydraulic pressure, which basically allows for it to be a little dribble or a gushing flow, depending on how it's set. Now, this is something that you will do every time you install a new hydraulic system, or even certain components of a new hydraulic system into into the aircraft. You'll make these little adjustments often sometimes even with just a jeweler's screwdriver. It doesn't take a whole lot to change the pressure in your hydraulic system with one of these pressure regulator valves. But this is a way to try to maintain the pressure at a stable amount that doesn't get too high, doesn't get too low. It's right there. Okay, so this is what it looks like whenever they are all put together in a kind of a simple hydraulic system. And you'll notice that all of the different parts and pieces are arranged to try to maintain a certain pressure. We're just kind of taking from the top down, and we're only going to be looking at the pressure regulation devices. So the filter is not that; it's just there to simply filter the fluid. Now, the constant delivery pump that's going to pressurize the fluid, pull it from the reservoir, and then push it down to the pressure regulator. Now, the pressure regulator, like we just looked at, is set to only allow a certain pressure into the system. So that way, if it's too much, it'll go to a return and go back into the reservoir, or maybe even be ejected from the system altogether. And if it's too low, then it won't be allowed to enter. Now, once it's through the pressure regulator and we have the right amount of pressure going in it, it's going to go into two check valves. Now, one check valve is to isolate the emergency hand put that also pulls from the reservoir, but the other one it sits on the other side and doesn't allow the system pressure to go back towards the regulator. Once it goes through that check valve, it's set in the system as at a certain pressure. It'll go down. You have a gauge, and then we eventually get to the selector valve, and the selector valve simply just allows for the fluid to go from one place to the other, but it doesn't necessarily affect the pressure that much. The one to look at is the relief valve itself. Now, the relief valve and the pressure regulator really basically are kind of similar in a lot of different ways. The regulator is purpose though is to regulate the pressure at a certain psi. The relief valve, however, doesn't have that regulatory function, but mechanically it's going to work much the same way. It's going to have a certain hydraulic pressure setting that's it's set at where if it gets anywhere above this, the valve will open and allow pressure out of the system to keep it from basically turning into a big pressure bomb. The mechanics of between the relief valve and the regulator work the same way. However, typically relief valves are not going to be customizable. You're not going to be able to adjust it up and down. It's just there as kind of a safety, much like the hydraulic fuse worked as a tourniquet. This simply works as like an open door. If there's too much pressure inside the system, that opens the door and lets some, if not all of the pressure out. Usually, it's just enough to let off that pressure, and then we'll reseat once the pressure drops below, because it's going to have a little ball check valve or a little ball valve with a spring on it. That's how that works. But that's your pressure regulation devices. Okay, so now that we've talked about the pressure regulation, let's talk about a couple of devices that get employed to use that pressure. First off, we're going to talk about like shuttle valves. Now, shuttle valves are unique in that they regulate where the supply of pressure is coming from rather than where it's going. Now, what a shuttle valve effectively does is it will allow for one pump or one pressure supply to channel it into the device or into the system, and then whenever they're activated, it closes that inlet off and opens it up to another inlet somewhere else. Now, the way that this gets employed on heavy commercial aircraft is that you always have multiples of pretty much everything. You'll have multiple hydraulic pumps. You'll have multiple accumulators, which we're going to talk about here in a minute. You'll have even the ram air turbine or the RAT that could potentially supply hydraulic fluid. Well, in the event of an emergency or a systems failure or any number of situations, you need a way to turn the failed hydraulic pump off and open up a valve for the working hydraulic pump or the RAT or whatever, and the shuttle valve is how that happens. So just keep in mind that as we go forward, whenever we're talking about like redundancies in hydraulic systems, the shuttle valve is really kind of like the linchpin for how that works. Okay, so really kind of the heart of a lot of your hydraulic system is going to be the accumulator. Now, what is an accumulator? The accumulator is a steel sphere divided into two chambers by synthetic rubber diaphragms. The upper chamber contains fluid at system pressure, while the lower chamber is charged with nitrogen or air. Cylinder types are also used in high pressure hydraulic systems, and many aircraft have several accumulators in the hydraulic system. There may be a main system accumulator and an emergency system accumulator. There may also be auxiliary systems accumulators located in various subsystems. What do they do? First off, they dampen pressure surges in the hydraulic system caused by actuation of a unit and the effort of the pump to maintain pressure at a preset level. And then they aid or supplement power pumps when several units are operating at once, supplying extra power from the accumulated or stored power. And then they store power for the limited operation of the hydraulic unit when the pump is not operating. They supply fluid under pressure to compensate for small internal or external leaks that would cause the system to cycle continuously by action of pressure switches continually kicking in. All right, so what does that exactly mean? So essentially, what happens is that the accumulator gathers up a bunch of hydraulic fluid, pressurizes it through air. Usually, it's going to you're going to have like a bleed air system that ties into it, or some, depending on the aircraft, some source of pressurization of that air on the other side of the diaphragm. Now, whenever there's hydraulic pressure that's needed, it comes from the accumulator, and it'll inject into it. And then now the pump is steadily pumping, and it's moving fluid back into it. And whatever device is pressurizing that nitrogen or air is steadily repressurizing the fluid as it comes in. And so you have a constant source of pressure from the accumulator. Now, when you go to work on any one of these aircraft, you'll see them all over the place. They're these massive balls. They'll usually have a dial on there. They'll tell you what pressure the air side is at, and yeah, so that's what they are. If you kind of look at the graphic there, you notice that there will be a servicing valve on the bottom. There's a retaining plug and a bladder that lines it. So you have like kind of the metal sphere that protects it, and the bladder that actually holds the air and hydraulic fluid. And they will just mount to the side like the 37. There's two in the wheel well. Okay, this is what a cylinder accumulator will look like. Notice it does the same thing, it's just in a different shape. But you'll see these in different places as you work, especially in smaller jets. I think it seems to be the place that you generally will see these types of accumulators. Most of the time, your heavy metal guys, they're going to have the spherical accumulators, and they're not small. They're very big. Okay, so how do things actually move with hydraulics? So you think about, you have like flaps, you have landing gear, you have all these different things that are hydraulically driven. what is like how do you take all of these pressure systems and valves and pumps and accumulators and turn them into actual linear motion that's useful? And the answer to that is the actuator. Now the landing gear system has several different actuators in there, but they basically break down into two kind of groups. One is a single action actuator, the other one is a double action actuator. And here is a graphic that explains those two. Now, a single action actuator has a spring in it that basically like whenever the pressure lets off, the spring then pulls the actuating rod back into the actuator itself. And that means that like you can only apply hydraulic pressure in one direction, and that means that whenever the hydraulic pressure is not applied, it wants to close on its own. All right. Now, a double action actuator will have hydraulic fluid on either side of the piston, and you'll have positive hydraulic pressure as it comes and it goes. And this is really useful. Think about like your landing gear extension and retraction. For one, to extend it down, you would need to be able to push it out of its place, hold it against gravity as it starts to fall down, and slowly like lock it into place. And then whenever you pull it back up, you need all that power to just simply grab it and pull it back into its place inside the aircraft body and let it lock in place. So that's where your double action actuators come in at. Now I'll tell you, the vast majority that I've ever seen have always been double action actuators. There's only very few cases where you'll come across a single action actuator. So you think about on the Bell 407, there's 3 hydraulic actuators up in the on the roof of the helicopter, and that basically controls all your flight controls. There's 2 for the cyclic, and then 1 for the collective, or maybe it was 1 for the tail rotor. It's been a minute since I worked on them, but either way, they have 3 double action actuators that will extend and contract in both directions equally, and that allows you to manipulate the flight controls of the helicopter with a lot of ease. If not, you'd be just fighting with push-pull tubes, and you wouldn't be able to fly very precisely. Matter of fact, it may very well be just unsafe altogether. Okay, and so not all actuators are linear actuators like that. Some of them can be rotary actuators, and this is most commonly found on like different types of doors, be it cargo doors, weapons bay doors. I mean, you name it. If it's opening a door via hydraulic pressure, very common that you'll see these sorts of rotary actuators in there. They'll only move a finite amount, just like your linear actuators, but they use instead of having a piston that moves backwards and forwards with a long arm on it. Instead, it will simply move 2 pistons on a rack and pinion gear type system. So the hydraulic pressure actually spins the pinion gear, which then moves the pistons one way or the other, and that's how a rotary actuator works out. So you'll see those as well. Okay, so here's another device that you'll find inside of the hydraulic systems, which are actually pretty cool. It's called a power transfer unit. Now, this is out of an Airbus aircraft. Notice that you have green system pump, yellow system pumps. They divide their different hydraulic systems up in colors, as opposed to Boeing does, like hydraulic system ones, or left and right, if I remember right. And so, anyways, the what the PTU does is that it will transfer power, but it won't transfer fluid. So you have independent hydraulic systems, which gives you a certain amount of redundancy. If there's a leak in one, you will be able to power the other system with another system without having to compromise or mix or mingle hydraulic fluids. It's looks fairly complicated, but it's really not too bad. Effectively, you'll have a pump that will turn the PTU. It's like a kind of like a PTO on a tractor. It basically turns a big shaft, which can then be coupled to the other system's pump to keep things running. And so just know that the PTUs out there. We won't mess with them a whole lot, as they are kind of unique to the aircraft that they're installed on, and they're also kind of well above the pay grade of the school. I would hate to know how much one of those PTUs actually costs to mess with, but maybe in the future. Okay, another little component that we needed to kind of cover real quickly is a heat exchanger. Obviously, with a lot of the friction that you're going to have in these pumps and actuators and things like that, you're going to get a lot of heat. And so this is a heat exchanger on 737 Max. It's simply like a radiator, and it's placed inside the fuel tank. And what that does, is fuel throughout aviation is always seen as kind of cold and will be used frequently to help cool things down. We'll get into more of that in power plant whenever we get there. But essentially, hot hydraulic fluid comes into the heat exchanger inside the fuel tank on either side, and then it gets routed through the fuel so the fuel can pull some of that heat away from that hydraulic fluid, drop it down so that way it goes back into the system nice and cool. Otherwise, you would have a serious problem with component failure and potential fires because that hydraulic fluid gets extremely hot, and you have to cool it down or else you'll suffer the consequences of that heat. Okay, finally, here is one of my favorite things on all heavy commercial aircraft is the RAT. Now, the RAT stands for the Ram Air Turbine. Now, what this does is that in case of a electric or hydraulics failure, you'll see the RAT get deployed, and it'll start to spin that little turbine, and that little turbine then adds hydraulic pressure to keep everything going. It also works like a generator and helps keep the lights on as you precautionary land wherever you can. Now, I'll tell you, for just from a safety standpoint, you don't want to be anywhere near this thing when it comes down because it comes down incredibly fast, and it's not small and it's not light, and so if you get whacked by that thing, it's not going to be a good day for you. And it's a cool little device that you'll only see on like heavy commercial aircraft. So enjoy working on those. All right, so the last kind of piece of the pie is just hoses, lines, and fittings. We've already covered this pretty extensively in general, so we're not going to spend a whole lot of time on it right here, but we are going to kind of give you the high-level overview of it just as kind of a recap. We're going to talk about the way lines should be ran, should not be ran, and things like that. Okay, so we're not going to go over the building of the lines or hoses and the fittings and things like that. We're just going to kind of give an overview of things to look for whenever you install it, because anytime that you are doing any sort of hydraulic work, you're always going to be installing flex lines and rigid lines. Now, on this graphic, it shows you a couple of scenarios where you could be installing a line that is the right way or the wrong way. So let's start with the top left. So the top left shows that you need to have some slack in a hydraulic line or really any flex line, no matter like where you're installing it. Reason being is that whenever the hydraulic pressure is applied to that line, it's going to want to expand. When it expands, it needs to have some slack in order to expand into. It needs some sort of breathing room, if you will. The one on the top, there is no breathing room. It's banjoed. It's super tight. So whenever that pressure is applied, there's nowhere for that pressure to go, and so the line is going to eventually bust. Now, it may not do it on the first time, it may not do it on the hundredth time, but over time, you're going to over fatigue that line, and it'll eventually explode. Now, this is something that I learned personally in the first couple of months of Iraq because we had aircraft that hadn't been really flown super hard for a long time, and a lot of people made these types of mistakes whenever they installed it. And so whenever we got over there and we started flying, 12 on, 12 off every day, a lot of the pressure got put on these hydraulic lines in a way that it hadn't ever been before, and so they started to bust and explode and have all kinds of problems. Now the same thing that goes for the one that is just below that, in the bottom left-hand corner. Those sharp bends, effectively, it's like banjoing a line. You need to make sure that you're inside of the bend radius of whatever the allowable bend radius is for your flex lines, because if you just do a hard 90 like that, then effectively in that 90 you have banjoed that line. There's nowhere for it to expand and contract to, and eventually it's going to bust. It's the two are the one on the top left and the one on the bottom left are basically the same principle applied differently. Now the one on the top right shows that there's a linear stripe that goes down a lot of those flex hoses, and you want to make sure that isn't twisted. The same concept, just applied again. If a twisted hose is twisted, there's nowhere for it to absorb the pressure as the fluid comes through the line, right? And so effectively that twist, I mean, you just think about taking like a drinking straw and twist it on either end, and it's going to narrow the inside of the straw because you're starting to roll it over on top of itself. Well, imagine that you pressurize that. Now, instead of being rated, say if it's rated for 10,000 psi, you've basically taken the rating down to 5,000 psi, but you've maintained the hydraulic pressure at that 10,000 psi, and there's nowhere for it to expand. And so now it's under what it should be able to hold by design, and it's there's nowhere for it to absorb that extra pressure, and so it's a surefire way to cause a break. Now, on the bottom one is showing you that whenever there is a weird angle or whatever else, you want to give it a little bit of extra room because the hose is having to contend with all that weird geometry, and you want to make sure that it is flexible enough, and you also don't want to put too much uh, um, oh slack in the line for a lot of the same reasons. Now, here's another thing to keep in mind. A lot of these, especially hydraulic lines, are braided. All right. Now they're not on the outside. You can have like braided cotton sleeves that go over the rubber hose that's on the inside, and then but most of the time with hydraulics, especially heavy commercial hydraulics, you're going to end up having steel braided lines on the outside. Now, whenever you see one of those plates, the kind of rule of thumb is that like no more than two wires from one of those little braid plates can be loose, or else the hose needs to come off and get replaced. Now that's a pretty aggressive maintenance practice, but the reason being is that like these things fail, they fail fast, and so if you see like one that comes loose, it could be a manufacturer issue, it could be just like a one-off, like I got hung on something during installation, eventually finally broke or whatever. But when you have two, that almost kind of indicates that there could be potentially something wrong with that. Now, if you don't change it then all of a sudden, like you could be in a situation where you could see it explode. The key to making sure that that does not happen is that it is installed correctly, and that it's also isolated from anything that it could rub up against correctly. And so, like chafing is a major concern with these types of lines and with rigid lines. So let's look at that. Okay, so this is a graphic out of the 8083 that's kind of addressing the right way to stabilize a hose. Now that could be a flex line right there, and it could also be a rigid line. They're using a grommet around the metal that's going to pass through, in case there's ever any sort of contact, it'll contact the rubber of the grommet rather than the metal. Anytime you get metal on metal with any of these hoses or lines, it is a death sentence. It doesn't take very long for them to rub through, especially if you're in a high vibe area. It'll go right through it. The one thing with this in particular graphic that's kind of not really realistic is that most of the time, especially whenever you're passing through like lighting holes and things like that, you're not going to have grommets for all of that. Things you can do is you can wrap some with some peanut butter tape. I'll see if I can get a picture for that. Okay, so with this, you're just going to simply wrap the hose as it goes through some sort of area where something could rub on it. And what you're doing is the tape will create a standoff distance between the actual hose itself or the line itself and whatever's chafing up against it. Now, over time, you might have to replace the tape, but the tape's not really that expensive, and it's really, really durable, so it takes a long time for it to start to fall apart. But this is something that you should keep in your toolbox, and most operators will have some sort of bench stock supply that you can just grab one of these, throw them in your toolbox, and then it's there whenever you need it. If not, then it'll be in your tool crib or whatever to go and get. But essentially, you just take the tape, stretch it out over the line, and then you put the outer layer of the tape as it comes back around to wrap on that center line, and it's adhesive, so it'll stick to itself extremely well. And that's why there's that plastic layer on there to keep it separated. So that's one way to do it. Another way that's a little bit sloppier, but it's a lot more versatile, is simply use RTV. RTVs. You have like red RTV and black RTV. Black RTV is kind of like the common stuff. Red is my go-to because it's high temp and it's chemically basically about the same. It just is a lot more resistant to temperature or to higher temperatures. So you're just getting like more bang for your buck, and they're not really that much more expensive. And most of the time, if you're working for like a big commercial industry or big commercial operation, they're going to have this stuff on hand. But if you get to a place where you can't clamp something off and you can't put snakeskin on it or peanut butter tape or anything else like that, a lot of times RTV is the way to go. And what it'll do is it'll set up and it'll make like a rubbery, I guess like kind of ball on whatever it's adhere to, and that creates that same standoff distance between the two things rubbing up against each other. And a little bit of this goes a long way because like you can just squirt some RTV on it if there's two clamps coming or two hoses coming together that you can't seem to get to stand apart in any meaningful way, or there's you get into situations where if you move this hose, then you solve one problem but you create another. RTV can be a way that you just shoot it onto the hose. It'll set up and create like a little rubber buffer zone between those two hoses and save them. Okay, another option is what's known as snake skin. That's kind of like the I don't know, colloquial name for it, but essentially like hose guards, plastic hose guards. That type of nomenclature is probably more proper. But essentially, what this does is it protects the hydraulic hoses from rubbing up against things. Now, I will tell you that just over time and experience, I do not prefer this on anything. It's not anywhere on my plane, and it's not if I'm working somewhere and I'm having to install something, I'll purposely take it off, throw it away, and try to put things on there that actually work a little bit better. What ends up happening is that it effectively doesn't do its job very well, and it'll hide a lot of problems that you could otherwise catch. And so one of the kind of the big moments for me to kind of turn me away from this is that we had a hose bust in Iraq that about caused us to lose an aircraft. Well, whenever we got to looking at it, we were like, and this had been gone, several months into that rotation, and we realized that hey, like we fixed a lot of hoses, and there shouldn't have been. We shouldn't have seen like another hose bust like that because we had gone through and really gone hard at making sure that all of our hoses were taken care of, especially in the hydraulic system, because in the OH58 it operates under about 6,000 psi if I remember right, and there's only has a quart of fluid. So the moment you get like any sort of leak, it just basically like blows all the fluid out, and then you're without hydraulics, and that's what happened in this flight. And what we realized is that we had seen the snake skin and thought the line was okay, and what it actually did was it hid a hose that was starting to fall apart underneath it. And whenever you inspected it, if you didn't pull the entire snake skin off and look at it, you would have never seen the hose degradation underneath there. Now with the other approaches, like even with the Dell clamps, you can push the hose down and kind of look into the clamp and see that if it's starting to like deteriorate or anything else like that. But with the snake skin, the way that it works is that it covers up the entirety of the hose, so you'd have to take that entire thing off, and it's not necessarily the easiest stuff to get on or get off. And especially like whenever you take it off after it's sat for a while, you can stretch it out and make it where it doesn't want to go back on. So then you're having to replace it all the time. And so just as a general rule, I try to stay away from this stuff and only use it whenever there's just not really any other option than to use the snake skin. All right, so this is probably the king dingling of all hose and line preservation is a rubber cushion clamp, or also known as an Adele clamp. Now these clamps are really good for a couple of different reasons. One, if you notice, there's a rubber grommet that basically cushions the hose and make sure that it can't rub up against anything that's metal. It also is very proactive. Like whenever you clamp down on this clamp and put it somewhere, it's not going anywhere. RTV could potentially fall off. Peanut butter tape could potentially degrade over time, and you're constantly having to to make it move. Adele clamps, the only problem you're ever going to have is installing them and uninstalling them, because they have a very strong spring action to them, and they can be very, very difficult to manipulate. And that hose or that rubber grommet will fail over time. But the good part about an Adele clamp is that it always fails in the corners, right there where it makes the 90 as it curls up onto the clamp itself. And so you can always see it really, really easily. And oftentimes you can push down on the hose and see into it, like I was saying earlier. And there are, whenever you get like a clamp kit, there comes with a gazillion of these different types of clamps. And so you can always make them work. And you can also, if a hose is rubbing up against something, you can clamp one thing off to, say, like an engine mount, and then on the other side you have your Adele clamp that actually holds the hose itself. And so you can customize a lot of this type of stuff to get the right routing for your particular aircraft, and that's perfectly okay. Like that is a very common practice throughout all of aviation, heavy commercial, military, GA. Everybody uses these things. Now, there is some special tools that will make your life easier. You don't have to have them. There's a lot of tricks to zip tying off the clamp. You put a screw through there and you zip tie it off so it holds itself, in place, or using safety wire for it. I've done all of it at some point or another. It's whatever will hold that clamp together while you manipulate it and get it all installed. But there is a pair of vice grips that has a special nose on it that will clamp down and hold those clamps in place. And then you always want to use a scratch awl to try to line it up. And so that's kind of like an idea. Like, the installation bit can be kind of a challenge with these things, but they are by far probably the most effective way at taking care of making you have the right hose routing and making sure that they aren't chafing against each other. Okay, so let's end on metal fittings and things that we should look at. Now, this is actually out of the 808330 for general on how to build the rigid lines correctly. The main thing I want you to take away from this is that what a good line looks like. Notice that it's nice and it's bent perfectly. There's no wrinkles in it. There's no dents, and there's no scratches. Now, generally speaking, you can flatten the area of the outer curve of a 90-degree angle, but it has to be within limits. And you can go back to the 8330 or AC43 and review those limits. The rule of thumb with the scratches on the outside of the tube, which you will see, and these things get scratched all the time in installation and just things coming and going in and out of those compartments, is that it can't exceed more than the scratch can't exceed more than 10% of the depth of the line itself. All right, so that means that, like, if it's an inch thick, or say like 10 millimeters thick, the scratch can only be 1 millimeter deep of the sidewall. Other than that, it's considered no good, and you have to replace the line. The good part about these is that the line is actually fairly easy to manufacture on site and replace. It's not that big of a deal if you have to replace one, and a lot of times, especially a heavy commercial, you're just going to order the part, and if it's a part that's known to get damaged, you'll probably end up having several on hand, because this is something that comes and goes on a pretty regular basis. Not that big of a deal, it's just cost of doing business. But yeah, so that is kind of like all the basics of hydraulics, and now we're going to talk about the operation, like why hydraulics works the way that it works, and what different types of systems are out there, and then we'll eventually apply it to the 737. Then we'll get back into how it applies directly to landing gear.